Hello everybody, it is May 28th and we are going to wrap up our acid and base unit talking about Bronstedlowry acids and bases and talking about titrations. The Bronstedlowry acid-base definition expands upon the Arrhenius definition. So as a quick reminder, Arrhenius acids release excess hydrogen or hydronium ions in water, and Arrhenius bases release excess hydroxide ions in water. So looking at the Bronstedlowry definition for an acid, we can say that a Bronstedlowry acid is any substance that donates a proton or positive hydrogen ion. It is called a proton donor, which should make sense, right? The higher the hydrogen ion concentration, the greater the acid. Let's look at a few examples of Bronstedlowry acids. Here we have nitric acid placed in water. When it is placed in water, it ionizes to become hydrogen ions and nitrate ions. So it's a hydrogen ion donor. And just as a reminder, these two equations represent the same phenomenon. We are donating, in this case, a hydronium ion, but that's that extra hydrogen ion in place here. Now, when we move on to Bronstedlowry bases, the definition is that it's equal to any substance that accepts a hydrogen ion. So a Bronstedlowry base is going to take up or accept hydrogen ions, thereby reducing the concentration of those hydrogen ions, making it a base. And this expands that Arrhenius definition because now substances that do not have that hydroxide ion associated with its chemical formula can be considered bases. So any substance that accepts protons, takes them out of solution, is considered a Bronstedlowry base. In order to look at Bronstedlowry bases, we're going to look at this equation here. So I still have my nitric acid, and I've just put the water in on the reactant side as opposed to on top of the arrow, which is perfectly fine. So you're going to note that when nitric acid reacts with water, it produces a hydronium ion and nitrate. This nitric acid is considered a Bronstedlowry acid, as mentioned earlier. Why? Because when it changes from this species to this species, it had to donate that hydrogen ion to become just the nitrate. So this is considered the Bronstedlowry acid. It donated that hydrogen ion. Now, this might surprise you a bit, but water in this case is actually acting as a Bronstedlowry base. Why? Because it's accepting a hydrogen. So we have two hydrogens here. It's accepting this hydrogen to become that hydronium ion. So in this case, water is considered a Bronstedlowry base. Now there's another little part to this here. The Bronstedlowry acid is always connected to a species, and it's called its conjugate base. So the nitrate is the conjugate base, because in the reverse reaction, this is taking up a hydrogen from the solution to become nitric acid. Likewise, water, the Bronstedlowry base. In the reverse reaction, this hydronium ion donates one of those hydrogens back here. So this is called the conjugate acid. And we can call these conjugate acid-base pairs. That's a conjugate acid-base pair, and this would be the conjugate acid-base pair. Okay, let's look at another example of a Bronstedlowry base. So we have ammonia reacting with hydrogen chloride to make the ammonium ion and chlorine. When we look carefully, we notice NH3 becomes NH4. This must have accepted a hydrogen to become that. Therefore, this is the Bl base. It's a hydrogen ion acceptor. That makes this the conjugate acid. Now, if we look at hydrogen chloride or hydrochloric acid and compare that to the chlorine, this must have donated that hydrogen to become that. So this is your Bronstedlowry acid. It's a hydrogen ion donator, and its conjugate base is the chlorine ion. And just another side note, with Bronstedlowry acids and bases, it doesn't always have to involve being dissolved in water or an aqueous solution. And this is one example of that. So the Bronstedlowry acid-base definition expands the definition of acids and bases beyond the Arrhenius definition. Now, to conclude this unit, our final topic is about acid-base titration. This is a very important technique that allows one to determine the molarity of an unknown acid or base. You must watch the 5-minute biorad video I have attached on the class Padlet. It is extremely important to witness the titration. We would have done this as a lab. Also, please note that on table T, we have a titration equation, which is MAVA equals MBVB, where MA is the molarity of the hydrogen ions in an acid, VA is the volume of that acid, equals the molarity of the OH ions in the base, versus the volume of the base. So let's look at this example problem. How many milliliters of 0.2 molar sulfuric acid, so we know that, are required to completely neutralize 40 milliliters of 0.1 molar calcium hydroxide? 40 milliliters of the base, the molarity is 0.10 molar. Okay, so we have 3 out of the 4 requirements for this equation. So let's look at that overall equation. The molarity of this acid is 0.20 molar. How many milliliters do we need? The molarity of the base is 0.10 molar, and we know the volume is 40 milliliters. Okay, so to solve for x, we divide both sides by 0.20, and we're going to end up with 20 mils of H2SO4 are needed to neutralize this quantity of base. That concludes our acid-base unit. I hope you enjoyed the lesson. Bye.